When designing controllers based on models obtained from machine learning, consideration of the model uncertainty is crucial. There are two ways to deal with the uncertainty: optimistic and pessimistic approaches. In the optimistic approach, we take a higher risk, which typically leads to more efficient policies. In the pessimistic perspective, we consider the worst case, which leads to conservative controllers, but gives us performance guarantees. Therefore, the question is if we can find controllers that are not overly conservative, but still provide, possibly weaker, performance guarantees. We approach this problem by considering control-affine systems, here, where we assume that the function f is unknown. However, we assume that a probabilistic model in the form of a probability distribution P with mean mu is available. The task lies in tracking a reference trajectory, which defines a set xref. Our policy for this consists of two parts. The first one is the feed-forward component, which uses the mean function mu, whereas the second part is the feedback component, which depends on a parameter theta. Our goal is to find feedback controller parameters such that the tracking error remains below a prescribed value, here denoted as E bar. We formulate this using the Lyapunov function v, as shown here in this expression. Additionally, we want to consider subordinate control design goals, such as low controller gains. This is expressed in terms of a cost function L, which is given here. In order to achieve this goal, we decouple the derivative of the Lyapunov function into a nominal, here, and an uncertain component, here. When we choose the feed-forward and feedback controller appropriately, we can make the nominal derivative negative definite. In contrast, the uncertain component can be positive, but is independent of the control parameter theta. We exploit this to formulate our design goal here as a robust optimization problem like this. However, the robust optimization problem here is generally intractable. Therefore, we relax the strict constraint here to a chance constraint like this. For this reason, we assume a uniform distribution over the states and the reference states, and additionally allow a small violation probability epsilon bar for the originally posed constraint here. Now, the problem can be approximately solved using scenario optimization. For this, we draw sample states, sample reference states, and sample uncertainties from the corresponding distributions here. Furthermore, we replace the originally probabilistic constraint by deterministic constraints here, but we enforce them on all the samples. Therefore, this optimization problem can be solved using standard gradient-based numerical optimization methods. However, theta star depends now on the random samples and thereby becomes a random variable itself. So what is the probability that theta star violates the chance constraint? And how should we choose the number of samples m? The answer to this is given by this theorem here, which requires us to count the number of active constraints. Then we can iteratively increase the number of samples m until the guaranteed violation probability eta is smaller than our required violation probability eta bar. We applied this approach to two problems. In the first one, we use a Gaussian process model for feedback linearization. Furthermore, we use a PD feedback controller with gain theta that must ensure a tracking error below 0.1. However, high gains should be avoided, which is expressed through the quadratic cost on theta here. We compare the results of the scenario optimization to a high gain controller with theta equals 10. As it can be seen here, the scenario approach results in a significantly lower gain in average. Also, for some GP models, a high gain is required, as indicated here by the 1. The smaller gains cause a slightly tighter tracking error in average, but all the simulations satisfied the desired performance constraint. In the second problem, we use computed torque control enhanced by a Gaussian process. The feedback controller is again a PD controller, but the gains are a state-dependent radial basis function network. The performance constraints and the cost function are analogous to before, and we compare to constant PD gains again. The resulting controllers from the scenario optimization show a similar performance to the constant controller as shown here regarding the tracking performance. However, they have the additional advantage that the performance is guaranteed with high probability. Therefore, our scenario approach for control parameter tuning allows to determine non-conservative, complex controllers with theoretical guarantees.